In what we have discussed so far, we have talked about inference problems arising in the context of multivariate normal distribution. Our focus so far has been on the mean vector of a multivariate normal distribution. We have talked about some testing hypothesis problems, and in order to settle the testing hypothesis problem, we have taken the likelihood ratio root, and as part of the process we have talked about in some cases we have derived also, we have talked about the maximum likelihood estimators, and finally we have obtained or at least stated the expression for the likelihood ratio statistic, or rather log likelihood ratio statistic, and also stated its null distribution, sometimes exact, sometimes asymptotic. Now we are going to discuss in the first of two lectures we are going to discuss inference problems about multivariate normal dispersion matrix. In this lecture, the first of two lectures, now we are going to discuss two problems. First, testing that the dispersion matrix of a multivariate normal distribution is equal to a specified positive definite matrix. So basically, if we denote by sigma the dispersion matrix of a multivariate normal distribution, then we are going to test or rather discuss the hypothesis testing problem of sigma is equal to sigma naught versus sigma not equal to sigma naught. This is the first problem in the first lecture, and in the second problem in the first lecture is testing sigma is equal to sigma square sigma naught, where small sigma is an unknown positive quantity and sigma naught is a specified P cross P, that is when P is the dimension of the multivariate normal distribution, P cross P positive definite matrix. And with all of this setup, we are assuming that we are made available a set of size n IID observations from a multivariate normal distribution of dimension P with an unknown mean vector mu. So these are the two problems we are going to discuss in this lecture. So we are addressing problems of inference about a multivariate normal dispersion matrix. In the first problem there are two problems that we are going to discuss in this lecture, we assume the same distribution theoretic setup. So let's be specific. We assume that x1, x2 up to xn are independent and identically distributed observations having a common p-dimensional normal distribution with mean vector mu and dispersion matrix sigma, where mu is an unknown p cross 1 vector, that is the mean vector is unknown. We wish to test the following hypothesis. So we recall that in the case of test about a mean vector, we had to begin with talked about testing mu is equal to mu naught. Now in the problem that we are addressing now, we are addressing the problem of testing sigma is equal to sigma naught against sigma not equal to sigma naught, where sigma naught is a known P cross P positive definite matrix. So let's ask ourselves what we have done so far. We have talked about descriptive statistics, maximum likelihood estimates, and so on and so forth. So what are the descriptive statistics in this case? Under assumption of normality, the following descriptive statistics are sufficient. What are the objects? First is sample mean x bar, and then sample dispersion matrix, which is denoted by S, and multiplicative factor is 1 by n. So we can see the expression for sample dispersion matrix. We also assume in particular that n is at least p plus 1. This is to guarantee almost sure invertibility of the matrix S. We recall that in many of the testing problems, in fact most of the testing problem, when we had to estimate sigma, we required in the case of univariate normal distribution, we needed at least two observations, that is to ensure that the sample variance is strictly positive with probability 1. So in the case of multivariate normal distribution, we should necessarily have at least p plus 1 many observations. All right. So this is our setup: multivariate normal distribution, then sample mean and sample dispersion matrix. These are the descriptive statistics, and these are sufficient under assumption of normality, and we have at least p plus 1 many observations. What we shall do now, we shall write down the likelihood ratio test statistic and also state its asymptotic distribution. So let's see what are the expressions for the maximum likelihood estimators. In order to find the maximum expression for the likelihood ratio statistic, we have to find, to begin with, the maximum likelihood estimator of mu under H naught. We don't have to bother about sigma because it is anyway under H naught. Sigma is known to me, sigma naught. So in the case of under H naught, that is when sigma is equal to sigma naught, the maximum likelihood estimator for mu is x bar, the sample mean. And when we don't have any restriction over either mu or sigma, then the maximum likelihood estimator of mu comma sigma without any restriction is x bar comma s, that is the sample mean vector, sample dispersion matrix. So let's see what is the expression for the likelihood ratio test statistic lambda now, and what is the asymptotic distribution. So let us recall that in order to obtain the expression for the likelihood ratio test statistic, we have to look at the maximized log likelihood under H naught divided by maximized likelihood without any restriction under the parameter on the parameter, and then take the ratio, and then we have to look at the minus 2 log lambda. Lambda is the ratio. Let's see the expression for minus 2 log lambda. Lambda is the likelihood ratio, minus 2 log lambda is known as log likelihood ratio statistic. This equals, in this case, one can derive it without much difficulty. This is equal to n times trace of sigma naught inverse S minus n times log of determinant sigma naught inverse S. We should notice here that determinant of sigma naught inverse S, this because already I have assumed at least p plus 1 many observation, ensuring S to be a positive definite matrix, and sigma naught by choice is a positive definite matrix. So sigma naught to the power minus 1s, its determinant is same as determinant of sigma naught to the power minus half s product sigma naught to the power minus half, which is strictly positive. This itself is a PD positive definite matrix. So the determinant is strictly positive, hence I can talk about log of the determinant. So let's see what the expression is again. Minus 2 log lambda is n times trace of sigma naught inverse S minus n times log of determinant sigma naught to the power minus 1s minus np. Suppose now we introduce, just let us look at the expression for minus 2 log lambda. These expressions, trace, determinant, etc. immediately remind us of let's recall the fact of linear algebra that trace and determinant are connected to the eigenvalues, and we immediately see that basically if we look at the trace is sum of eigenvalues, determinant is product of eigenvalues, so we can immediately associate this expression minus 2 log lambda with arithmetic mean of the eigenvalues of sigma naught to the power minus 1s, sigma naught inverse s, and the geometric mean of the eigenvalues of sigma naught inverse s, which we denote by a and g. So arithmetic mean of the eigenvalues is a, geometric mean is g. Then it is easy to see that this a is equal to p inverse trace of sigma naught inverse s, and g is equal to determinant sigma naught inverse s whole to the power 1 by p. And then we immediately notice that minus 2 log lambda is np times a minus log g minus 1. And what is the asymptotic distribution? This is the asymptotic distribution of minus 2 log lambda under H naught, that is the null asymptotic distribution, is chi-square distribution with f degree of freedom, where f is equal to p times p plus 1 by 2. Okay. So this is what we see now. We have been able to obtain the expression for the log likelihood ratio statistic for this problem, where we are testing sigma is equal to sigma naught based on n IID observations from a multivariate normal distribution with unknown mean and at least p plus 1 many observations. We have been able to obtain expression for the log likelihood ratio statistic for this problem, testing sigma is equal to sigma naught, and we have also been able to state the asymptotic null asymptotic distribution for this test statistic minus 2 log lambda. All right. Now we shall go to another problem of the similar flavor. It is slightly general than a same kind of problem that we see in standard texts. We shall have occasion to come back to that problem in the next lecture, but let's go to the problem that we wish to discuss now. Let us look at the second problem to be discussed in this lecture. It is of the same flavor and distribution theoretic assumptions are same. Let's see. So we, as before, as in the first problem, we assume that x1, x2 up to xn are independent and identically distributed observations having a common multivariate normal distribution in p dimension with mean vector mu, which is assumed to be unknown, and a dispersion matrix sigma. And we shall be talking about discuss some testing problem about sigma. And we wish to test the following hypothesis. What is the hypothesis? Sigma is equal to sigma squared times sigma naught. We shall look at a very special case of this problem in the next lecture, but before that let's discuss the somewhat general problem. So we are testing sigma is equal to sigma squared times sigma naught against H1. The alternative is H0 is false, where sigma naught is a known P cross P positive definite matrix and small sigma is a strictly positive unknown quantity. This is the hypothesis we are testing. And what are the descriptive statistics? Basically our path is same. We are looking at the likelihood ratio statistic. In order to find the likelihood ratio statistic, we are looking at finding the maximum likelihood estimators, and before that we identify the sufficient statistics. That's how we are proceeding. So under assumption of normality, the assumption that we have already made, sample mean vector x bar and sample dispersion matrix S with a multiplicative factor 1 by n in the summation. So sample mean vector and sample dispersion matrix, these are the sufficient statistics. We assume that there are at least p plus 1 many observations. We have discussed before that this will ensure almost sure invertibility of the sample dispersion matrix S. So as we are always doing, we shall mention the likelihood ratio statistic, or explicitly the expression for the likelihood ratio statistic, and also state its asymptotic distribution, null asymptotic distribution. So let's see, as we have noticed time and again that in order to obtain the likelihood ratio statistic, we need the expression for the maximum likelihood estimators. So what are the expression for MLE, maximum likelihood estimator? So when under H0, that is when sigma is of the form sigma squared times sigma naught. Sigma naught is a known P cross P positive definite matrix and small sigma is a strictly positive unknown quantity, and mu, the population mean vector, is unknown. In that case, the maximum likelihood estimator of mu comma sigma squared, small sigma square obviously, under H0 is x bar comma trace of sigma naught inverse S divided by P. And when there is no restriction on the parameters mu comma sigma, we know that the MLE is given by x bar comma S. So this as the background knowledge. Now we are in a position to obtain state the expression for the likelihood ratio statistic, which we are denoting by capital lambda, and its null asymptotic distribution. The expression for the log likelihood ratio statistic is given by, so the expression that the notation is -2 log capital lambda. This is equal to NP times log a suffix 0 a naught minus log g naught, which is same as NP times log a naught by g naught. So let's see what are these quantities a naught and g naught. A naught is arithmetic mean of the eigenvalues of sigma naught inverse S, and this is equal to the trace divided by P, because sum of eigenvalues is a trace, and g naught is the geometric mean of the same objects, that is the eigenvalues of sigma naught inverse S, which is equal to determinant sigma naught inverse S whole to the power 1 by P. And we can readily see that if we recall the expression for the sigma hat square, and if we compare that expression with this A naught, we shall immediately see that A naught is equal to sigma hat square. So let's see, we reject H naught if A naught by G naught is too large. A naught is anyway large, bigger than G naught, because we from the arithmetic mean geometric mean inequality of positive quantities. But if the ratio of A naught and G naught is too large, we reject H naught, because in order to reject the hypothesis H naught, we must have -2 log lambda large, and that's a strictly increasing function of A naught by G naught. So in order to reject H naught, we should demand that A naught by G naught should be sufficiently large. And the asymptotic null distribution of -2 log lambda, that is the log likelihood ratio statistic, is chi-square distribution with f degrees of freedom, where f equal to p minus 1 into p plus 2 divided by 2. Thank you. So let us conclude now of this first talk. So let's begin by recalling what we stated in the introduction. We are talking about dispersion matrix, inference about dispersion matrix, and the dispersion matrix denoted by sigma. What we have discussed in this lecture, first lecture, is we have talked about two distinct problems. One is testing sigma is equal to sigma naught, a specified positive definite matrix, and in the second problem we have discussed sigma is equal to small sigma square times sigma naught, where sigma naught is a specified P cross P PD positive definite matrix, and sigma is a strictly positive quantity. And what was our root? Our root was the following. We have taken the root of the likelihood ratio statistic. In order to obtain the likelihood ratio statistic, we have first of all we have actually stated the expressions of the likelihood ratio, maximum likelihood estimators of the underlying parameters. Sometimes the parameters are partially known, sometimes they are completely unspecified, especially if we look at the expression for the likelihood ratio statistic itself. In the denominator, nothing is known. So that was our first step. Once we obtain expression for maximum likelihood estimators, then we obtain expression for likelihood ratio statistic, and then we state the asymptotic null distribution, or sometimes exact null distribution can be obtained, but the testing problems we have discussed today in this first lecture, there was no such option. So that's where we conclude the first lecture. Thank you.